time for
chemistry.
Yeah, baby.
Hi guys, total hard floppage on the old live today. I messed up the timing, so yeah, don't know what's going on with me today. Completely messed up the time of the live. Yeah, wasn't sure if I was supposed to go 6 or 7, and then on top of that, I think it was down at like 2:20 or something like that. So proper hard flop on the timing for this one. Hello. Yeah, gonna go over EZ isomerism today. I don't think this screen is like doing it for me at the moment, I'm telling you that much. Oh my days, what the fuck? Yeah, I don't know what's going on with my screen either. It's all a bit all over the place. Covering EZ isomerism. I am going to start doing GCSE lives at some point as well. But I'm going to do EZ isomerism, which is also known as geometrical isomerism today. But if you have any requests, I can go through some stuff if you want to go through some stuff. But yeah, the poll was for EZ isomerism. So yeah, I'm going to go through that first of all. So I mean, we could go through that in like 10 minutes, 15 minutes, 20 minutes, whatever. So EZ isomerism. Okay, so EZ isomerism is something that you'll come across in AS, but it will come up in A2 as well in exams, and it comes up in A2 when you do sort of complex ions and you do things like that. So when you have octahedral complex ions and when you have square planar ones, you have to be able to spot if it's cis or trans. Cis or trans and EZ are the two types of geometrical isomerism. Okay, and what makes geometrical isomerism unusual is that they have the same molecular formula, they have the same structural formula, so everything appears to be in the same place, but they have a different arrangement in space. So, and this arises, I want to show you here what I have. If you can see these two molecules on the screen, I have but-2-ene and I have butane. You see there's 1, 2, 3, 4 carbons there. Now what can happen with alkanes and with most molecules is that you can get what we call rotation, and what that means is this CH3 group here, well, this is all in like a tetrahedral structure, obviously, because there's 4 bonds around this carbon. This can rotate like that, and before you know it, the CH3 can be down there and that can be the H, so it can just rotate and spin like so, and the same can happen here. So 1 minute the CH3 can be there and then the CH3 could be down there on butane. So around each carbon the bonds can rotate around single bonds. You don't get that with the alkene carbon double bond. There's no rotation. Now in your exam board you don't really need to go into the detail of why there's no rotation, okay, so you don't need to go into all the orbitals and talking about all that. You just need to know that this is a planar molecule, and with planar molecules you don't get rotation around the bond. And so what it means is that once this has formed with the CH3 here and the CH3 here, this CH, what? 1 second, people, my screen is doing a funny thing. Okay, we are back. Okay, so what I was trying to say before the screen was rude to me is this CH3 here cannot suddenly rotate like that as the molecules are turning and spinning, the different atoms within the molecules. It cannot rotate and appear down here. That can't happen. There's no rotation. So more or less there's a 50-50 chance when this molecule is formed that the CH3 will be here or that it will be down here, and once it's formed there it's locked onto that side of the double bond. So what you have to know for your exams is that EZ isomerism, in this case you can also call this cis and trans isomerism, forms because there is no rotation around the double bond, and that's really the key thing you have to be able to say. No rotation around the double bond, and that's why we get EZ isomers. Now, on some exam boards, they just cover cis and trans. If you're doing the AQA chemistry exam board, you do EZ. I can't remember if they do that in OCR and EdXL, but cis and trans, what does that mean? So let's have a little look. Oh, let me put up a, so, okay. So, here's a little bit of explanation, not that you probably need it, but just in case, this is like, so EZ or geometric isomerism. Geometric isomerism, don't ask me why there's no bracket there. Anyway, don't check these for notes. But half of that's missing off the screen. Let me put that on there, right? Is that actually on the screen? Oh, well, never mind. We'll go for all of that anyway. There's some notes there for people that like notes anyway. So here are the two versions of but2ene that can be formed because there is no rotation. So if it forms with the two methyl groups on but2ene, these two CH3 groups there, and these two hydrogens here and here, it will be locked into that position, and it's a planar molecule. This means unlike butane, which has pyramids coming off of each carbon, so 3 dimensions, this is all a flat molecule. So on this side of the double bond, you've got the two CH3s, and on the other side the two H's, whereas with this one, the CH3 has randomly formed on that side, and that one has formed on that side during its formation. So you've got two forms of but2ene. How do we tell them apart? So the EZ isomerism, by the way, is just a more nuanced, more advanced way of saying cis and trans. Cis and trans, cis is like sisters, so this would be cis but2ene, but we're going to call it Z but2ene. And the Z but2ene, hold on my days, let me just make that bigger. Right, Z but2ene tells me that the double bond obviously is the most important thing here. That's on the second carbon. Give it the lowest numbering order. Z stands for Zusammen, which sisters, so they're on the same side of the double bond. Let's bust out the next one. And this one is entagen, E for entagen. Entagen. Oh my gosh. And so we're going to call it E but2ene. Anybody got any questiones about this one? So this is but2ene, and I'm going to put some questions up to go through once we go through this. So we got Z but2ene and we got E but2ene. Okay, E means opposite, entagen means opposite. Now EZ is just a little bit more nuanced. So when I was doing my A-level chemistry, there was no such thing as EZ isomerism. It hadn't been invented when I was doing my A-level chemistry in the very early 90s. It wasn't on the syllabus. So it was just cis and trans. So we would call this sister cis but2ene, and we would call this trans, meaning trans across the double bond. They're opposite each other. But it turns out there are other isomers, geometric isomers, that we couldn't label like that, cis and trans, and so we have to use the EZ isomerism, which means that even if you don't have two identical groups like this and this, you can number it with 4 completely different groups, as we're going to do. What's up, Gugatti? Draw all the possible isomers of butane or butene. Do you mean butene? Butene or butine? Yeah. Butene. Well, then we've got to go into structural isomers as well. So then we'll have like 2-mether whatever. So yeah, we can do that if you want, but let's get through the geometrical isomerism first, and then you could draw all the possible structures of butene. So you're going to have but1ene, and then you've got but2ene, you've got the E and the Z, and then maybe we can bust a methyl group somewhere in the middle. We'll have a look at those in a second, but That's not what we're here for. We're here for the geometric isomerism, but we can delve into structural in a little bit. So here's where it gets a little bit more complicated. You are important 452. You just got to work out how you've just got to work out you got to just get your pen out and work out how many isomers. There is no way to work out just off the top of your head like, oh, this is the number of isomers I can make. There isn't really a formula. No, there's not an easy way really. You just got to play around with them in your head, and yeah, you just got to play around with them in your head. So you've got positional with butene. You've got the functional group, and there's only two different positions of the double bond. It can either be butene or but1ene. There is no but3ene because that would make it but2ene. If you put it on the third carbon, you would then number from the other side. You always give it the lowest number possible. So with 4 carbons, but2ene can either be but1ene or but2ene. So you'd know there's only 2 positional isomers there where you can change the functional group. But then if you have but2ene, there's 2 geometric isomers, which I just showed. There's Z-butene and E-butene, depending on the arrangement of the particles around the double bond. We're going to look at this one. Bromo, you wouldn't get bromine to butene. That's now throwing in a bromine atom onto the alkene, so that's not going to help you. You can bromo-butene. Well, you would have to, the problem with what you've written there, Gugati, is you'd have to number. You need a number before the ENE because you don't know whether that's but1ene or but2ene. So you have to specify with butene whether it's but1ene or but2ene for the position of the double bond. Well, that's what we're doing today. We're going for a little bit of the naming. So, although this is, I can do a whole hour on nomenclature. Maybe next week I'll do naming. But yeah, this is going to be difficult because check this molecule out. You'll get a boom if you can name this molecule. Yeah, so as soon as you see a double bond, you can check to see, can it have geometrical isomerism? And what I mean by geometrical is can it be cis and trans or E and Z? Now we don't tend to use cis and trans much. We use it a little bit later on, but EZ is very similar, but EZ is slightly more nuanced. So they're just 2 naming systems for geometrical molecules, and they only occur when there's no rotation. Now, there's no rotation around the double bond, and if I have this bond here, this is a planar bond as well. That's the carbonyl bond you'll find on ketones, aldehydes, carboxylic acids. That restricts rotation as well. However, they can't get involved in cis and trans or E and Z, which we'll see why. So what we're looking at here this gets a little bit complicated. In order to have EZ isomerism, what I should have done. Okay, let me come here before I come back to that molecule. I'll come back to that molecule in 2 seconds. What I want to know is, before I go back to that disgusting molecule, can this molecule display EZ isomerism? So if we draw the formula of this out like this, you're going to have to put in the chat if you think this molecule can do EZ isomerism. Oh, I think someone's bossed out what that molecule was. Hold on. Let me check it out. Have I written that out? I don't think I've written that out properly. What's that? 1, 2, 3, 4. Have I put 4 carbons in the house? Yeah, I have put 4 carbons in the house. Have I drawn that out properly? That looks proper. Okay, cool. So, got a question here. Can this do EZ isomerism? While you're thinking on that, let me check out people's naming. Someone has put bromo, chloro, 2-mether-butene. Close, but you haven't numbered the butene. Marwa has put E, antigen, 1 bromo, 2 chloro, 2-mether-butene. You've got to number that double bond as well there, Marwa, to tell people the position of the double bond, but I'm going to come back to it in a second. Can this one do EZ? The reason why I wanted to bring this one up is no, it can't. So what you want to look out for, the answer is no, And the reason, that was a real crap highlighter. Let's try that. The reason, so when you're looking, the first thing to look for, can it do EZ isomerism? You want to tick off two things. First of all, you want to ask yourself, does it have a, or does sit, what the hell? Right, let's write that again. Does it have a carbon-carbon double bond? Tick. And then our second thing, are there different groups? I'm just going to say it mustn't have the same group on the double bond carbon atoms. That just sounds crap, doesn't it? Let's say that again. It must have different species. That's crap, isn't it, as well? On the carbon atoms, on each carbon atom of the double bond. Oh my gosh, on each. I should have thought about this, shouldn't I? Each carbon atom. So what do I mean by that? Listen, it can have an H here and an H here. That's fine, right? Check back here. Look, these guys, CH3, CH3, that's not a problem, but they're not on the same carbon. So each of the carbons, call them carbon 1, carbon 2, or carbon A, carbon B. Carbon A and B, or carbon 1 and 2, the double bond carbons, mustn't have the same group attached. So this one has the same groups attached onto the same atom. So that is a big fat no. It doesn't fulfill this requirement here, okay? It meets that. It's got a double bond. So that's what you want to look out for. That will not be able to do EZ isomerism. Right, check. We're going to go back to this disgusting one here. Okay, someone said Z1 bromo. Z1 bromo, 2 chlora, 2 ether, 1 methyl, but 1 ene. That can't be 2 ether, 1 methyl important, because if it's 2 ethyl, that's 2 carbons. And then the methyl's a carbon, and then the but is 4 carbons. Yeah. Let me go through and name this one for you. But what I should really do is show you how to name it. So I'm going to take you through how to name this. So first of all, I want to decide, is it E or is it Z? Now there's 4 different groups. So what we do is we go with the atomic number, and we decide which one has the highest atomic number on each carbon. So I'm going to call this carbon 1. In fact, I shouldn't really call it carbon 1, because then when I get to naming it, it's going to be a pain in the ass. Actually, it is carbon 1, because that's where the double bond is. But okay, so I can call it carbon 1. I'll call this carbon 1, and I'll call this carbon 2. Boy. Right, so I could have called it A and B. So we look at the first carbon, and we look at the 2 groups on the carbon. Which one has the higher atomic number? And what you're going to find is bromine has the highest atomic number. So we call this, we say it is HP source, it's high priority. And then we come to this chlorine and we say you are lower priority, you're not as important. Okay, now we then come to carbon number 2, and we look at this, and this is a carbon which has an atomic number of 6, but this one also has an atomic number of 6, so it starts to get a little bit complicated. Okay, they've got the same atomic number, but then what we do is we go to the next atom attached, and this one has another atom with 6 attached to it, another methyl group attached, and this doesn't have any group attached, so this bad boy is going to be low priority. So some people do it like that, or they add up the atomic numbers of the chain, and so that's 6 and then another 6, so they might say, oh, that's 12 compared to 6, but whatever. So essentially that's low priority, and this is high priority. Now you treat these high priority groups as being like 2 identical groups. So this is going to be Z isomer. Okay, so this isomer begins with a Z. Why can't the molecule in the picture rotate its double bond freely? Are you talking about this one? So it's to do with pi orbitals restricting the rotation. So it's to do with single bonds can rotate when you have the formation of the pi orbitals, which you get with a double bond. You kind of basically, you have electrons above and below a so you have a sigma bond going across here, and then you have unhybridized pi orbitals above and below the double bond. It starts to get a little bit complicated, but what you need to know is that that double bond is restricted, and so it's really that atoms cannot rotate around it. There's very little rotation. I'm not saying that can't move at all, but we like to call it restrictive rotation. So that chlorine cannot rotate and be vertically up there and then rotate and go down here and swap places with the bromine. They can't do that around the double bond, and it's because there's basically these things called pi orbitals vertically. I mean, are they vertical? They are perpendicular in terms of the internuclear axis across here. If you think there's a nucleus there and a nucleus there, you've basically, these electrons that are buzzing around here, you basically get kind of electron density there, and that basically restricts these guys moving. Anywho, yeah, it all gets a bit complicated, so let's stay out of that. This is a Z isomer, and you don't need to know that for your spec, depending on what spec you're doing, actually. So this is a Z isomer. Right, you're with me, guys. Z isomer. Now what we need to do is I need to decide what the bulky main chain is. So it's going to be 1, 2, 3, 4. This is my longest chain, right? So it's bute. So I'm going to write, maybe I should write bute over here because we know we're going to get messy with the side groups. So it's going to be bute, and the double bond is on the first carbon. So it's going to be bute 1-ene. Hopefully everyone cool with that. Give me bute 1-ene. Does everybody see what I did there with the high priority and low priority? Anybody got any questions about the high and low priority? Yeah, basically, yeah, it's rigid. Oh, Charning Gold Prelog, CIP rules, CIP rules. I'll come to that. We'll go through. I've got a question we'll go through on that with all the mark scheme, and you can see all the perfect way to word it. So this is a Z isomer, and it's bute 1-ene. Alphabetical side groups, people. Now try and name it. See if you can name it, but alphabetical the side groups. So chloro must be before bromo must be before chloro, and methyl must be last. So what would your name be now? See if you can name it now. With bromo, then chloro, then methyl. So how would you name it? The CIP rules. CIP is the abbreviation. Charning Gold or Carning Gold. I think it was a German guy or team that worked on it. And basically the rules are that you look at each carbon atom individually and you decide which group that's attached to it is the high priority group. The one with the highest atomic number is the high priority group, and the one with the lowest atomic number is the low priority group. If the two high priority groups are on the same side of the double bond, it's going to be zusammen, or like it's basically like cis. It's going to be zusammen, and if the two high priority groups are diagonally across the double bond from each other, it's going to be entogen, E, which means opposite. So this is, yes, only for geometrical isomers. Absolutely right. And the EZ isomerism, yeah, so it's only for geometrical isomers, but you will use it in A2 if you depending on if you're AS or A2, you will use it, and I'll show you an example. You will use cis and trans, which is, so geometrical isomerism is either EZ or cis and trans. Cis and trans is an older naming style that is slightly more limited because it has to deal with identical groups. This was a new way invented to say, well, look, this can form like this, or the ethyl group, it can form like this, or it can form with the ethyl group there and the methyl group on this side, and it will be locked in that shape. So it can be locked in that shape, or it can be locked in the shape with the bromine up there and the chlorine down there, and it could be locked like that, and that would create a kind of, yeah, so it allows us to expand geometrical isomerism to include molecules that have 4 different groups attached. Okay, so the proper name to this now, guys, would be Z, what are we saying, 1, Oh my gosh. No, not 1-chloro, you dipstick. I'm going to type it. By the time I actually write that out, the chances of me getting it right are very small. So let's type it out. It's going to be what? 1-chloro, no, 1-bromo, B before C, 1-bromo, 1-chloro, 1-bromo, 1-chloro, 2-methyl, M comes after, so 2-methyl. And then bute. I don't really need a capital B there, do I? Butene. Oh gosh. Yeah, you get the idea, right? I'm never going to get that right. There we go. So this is Z, which means the two high priority groups are on the same side. Z, 1-bromo, 1-chloro, 2-methyl, bute, 1-ene. Everybody cool with that? All right. Just in case you're thinking, what the blah? Here is a 6 marker. By the way, can you put in the chat if you're AQA or if you're studying the AQA chemistry exam board? Sir, does the length of the carbon chain matter for priority or just the immediate next atom? So the length of the... that's a really good point about does the length of the carbon chain matter? You just check the next atom, and so in which case the length of the longer the carbon chain will, as a side group, will have the higher priority. So an ethyl or a propyl group will have higher priority over a methyl group, and a propyl will be higher priority over an ethyl. But you could have a chlorine attached on the end there. Then you go to the atomic number of the next. So say I had CH3 and I don't know, or a chlorine attached to that, and then I had CH2Cl or CH2 with a Br attached or something, then the one with the Br would have the higher atomic number. So you just go to you can look at the group and see which one has the highest atomic number, basically, overall. Okay, so your AQA important 45. So this has come up twice, or maybe 3 times in total, and it came up in the last couple of years as well in an A2 exam. So it's a 6 marker, and it basically says explain how the Chan or Khan in gold prelog CIP priority rules can be used to deduce the full IUPAC name of this compound. Now what I need to do is just make this bigger. Excuse me while I make this bigger. Blah. Because you might not be able to see that on your screen. So, how would you name this? Now, this doesn't ask for the name. This doesn't say name it. Although, maybe it does imply it when it says how would you deduce it. It wants the explanation, and this has happened 2 or 3 times. 6 markers saying explain how to use the rules. So you need to have this clear in your head if you're AQA. Can you talk through an examiner and explain to them how you would name it? It's not just about you getting the name right. You've got to talk it through. So what I would say is, look, we're going to find the longest chain. So 1, 2, 3, 4. No, that's not the longest chain. 1, 2, 3, 4, 5, right? So to me, the longest chain, 1, 2, 3, 4, 5, you're looking at pent. Okay? So at some point, you might want to say, hey, the longest carbon chain is 5, so it is pent. And that might get you a mark. What else do we need to say? What I would say is, look at the first carbon. Now, you can call these carbon A and carbon B. It's up to you. Or you can just say, looking at one of the carbons, you just name a carbon. So I like to label them so that when I'm writing my answer, I can refer to like carbon A, or I can say the first carbon in the double bond. It's up to you how you want to name it. But that's not going to be carbon 1, so it could get confusing. So you might want to use like a letter. So it's up to you, because that is actually carbon 1 in the chain here, this one. So it's up to you. But what I would say here, I would say looking over here, first of all, let's look at carbon A. And what can we say? Where's the high priority? Which one is higher priority? This CH2OH or the H? Which one is the high and low? So you're going with Z3-methylpent2N1-ol. You might well be right with that, but remember we got to talk it through. So yeah, so we would say to the examiner, look at the first carbon, higher priority group is on top or above the double bond. It's not really above, but you know what I mean. And the low priority is the H. So you tell them the high priority is the CH 2OH. Now I'd want to explain why, and I would say because carbon has an atomic number of 6, hydrogen has an atomic number of 1. You're spelling it out to the examiner, why that's high and low. And then what we're looking at here, guys, this one is obviously low again. Now here it's more tricky. You want to say to the examiner, the methyl group has an atomic number of 6, but the ethyl group, the carbon is 6, and then you could say the next carbon is 6, so that's why. Or you could just add up, if you want, you could add up the total atomic number. You could add up the total atomic number and say this is 15, whereas this is 29. Some people prefer that. Would that make it easier for you guys? If that makes it easier, you're allowed to refer to it like that and say, well, the ethyl group has a total atomic number of 29, whereas this has an atomic number of 15. So low, low. So immediately we now know, as who said this was Z? I'm probably not going to pronounce your name at all right. Satya. Oh, yeah, I'm not doing well there. Satya Jitbura. Yeah, no. Okay, whatever. My pronunciation. Not right. Lower priority, below, higher up top. So you're right. It's Z, 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 Z. Now, so we go. That's Z, and the discussion of that is probably worth 3 or 4 out of the 6 marks. Just discussing how you worked out the high and low priority. And then what we want to do, main chain is going to be pent. It's going to be pent-2-ene. And then what have we got? Pent-2-ene. 1, 2, 3, 4, 5. 3 methyl. Yeah, we've also got an alcohol there as well. And it depends who takes priority. Yeah. So, no, we're prioritizing by atomic number. I mean, it doesn't really matter if you did it by mass either, but yeah, by atomic number. But I mean, it's going to end up being the same thing anyway if you did it by mass or atomic. Oh yeah, sorry. Yeah, good point. Thank you. Thank you. See that didn't make it simpler. Well spotted. Well spotted, Canish. So this would be 9. What would that be? 8 plus 9, 17. Well spotted. So you could do it like that. What I'm saying is you could work it out like that if you like. Personally, I was always taught you go to this carbon atom, then you look at the next one and see which one has, because this one might be extended as well, and you do it like that. But you can also do it by adding up all the atomic numbers of the whole group. So yeah. But well done. Yeah, well spotted for my deliberate mistake. Okay, let me put the answers up, right? Hopefully they've actually named it for us. So, did they actually name it? 3-methylpent-2-N1-ol. And that means, yep, you were correct. And it's Z. Yeah. So there you go. Maybe you guys can see that. Hold on. Give me one sec. If I cut that and then paste that, that's going to come over the top. So there you go. So that would be the answer. So you can see most of the marks, actually you've got about 4 marks out of 6 for just explaining the priority business, the Charning Gold, the SIP rules. That gets you about 4 of the marks. It's just like really stage 3, the conclusion that it's Z even gets you 5 marks. The final name is only 1 mark. So yeah. All right, let me give you some questions, guys. Let's do some questions on it. Okay, yeah, absolutely right, randoms. Absolutely right. That's how I do it. So that's how I do it. I consider the next group, but I have seen people now in mark schemes, they have started to say you can just add up the total atomic number of the group and compare the 2 groups. Like you can add the whole chain up, which is kind of the same thing. Personally, I would go check the carbon is 6. What is the methyl group attached to? Just hydrogens, which is 1. Whereas the carbon in the ethyl group is attached to another carbon so you go to the next one along in the chain and you check that one's atomic number. So I would do that, but I've seen people do it where they just add the total atomic numbers up. So that's just a new way that some people are doing it. I was always taught to go to the next group. But yeah. And if the ethyl group on the left was a propyl group, would our main chain change? Double bond plus OH always indicate the parent chain. Just a thought. So what's that? If the ethyl group, let me have a little looky. Yeah, if that was a propyl, then our main change, it wouldn't be pentene, it would be hexene, right? And then our numbering would change as well. Yeah, if it was a propyl, that would still be the main chain, but our main chain would change to hexene instead of pentene. Yeah. There's EZ. EZ is in IUPAC. You use EZ. The Z came right at the end somewhere here. I don't know where they put it, but yeah, deciding whether it was Z or not. So the isomer is Z is there in conclusion. So yeah, you had to decide on that. What was that? If the ethyl group, our main chain would still be the double bond. Yep. Yeah. The double bond would dictate the parent chain. Now, I have put up before the order of priority when it comes to naming things, when to know when to use the term hydroxy or when to know when to use whatever terms. But obviously, the alcohol group is going to be the one here, carbon 1. So that's why it ends up being pentuene. Right, let's have a look at some questions. Oh, good luck, Elliot, for your bio mock. Good luck. Is it a paper 1 or paper 2? So, one of these compounds cannot do stereoisomerism. Oh, by the way, stereoisomerism. Yeah. Stereoisomerism can include optical isomers, which are the enantiomers, the mirror images. But, so you would have to work that out. Yeah. Oh, gosh. Which one can't do stereoisomerism? Paper 2. Paper 2. I do have a couple of paper 2s up. I haven't put the 2024 paper up. I just started working through doing the 2024 paper 2. I only did like 3 questions. I haven't put it up. I've been doing like combined science GCSE ones. Hold on a minute. You're saying A can't do it. Let's check it out. I think this is a bit of a cheat. This question is a bit naughty of me because I think this is including optical isomers, but let's have a little look. So we've got propene. And if it's so propene, what we got? 1,2-dichloropropene. So we've got a chlorine there and there. Oh no, this could do optical isomer. Oh, where did I get that extra? Why don't I have? Why have I got an extra bond there? Jeez. What have we done here? That should be a carbon, right? Yeah. Okay. Yeah, that could do cis trans. Yeah, I've done all the other combined papers actually. So if you check it, I've done on the my combined playlist. I think there's only one combined paper I haven't done yet, like Physics 2019 or something. Propene. So this one, oh, it's probably not large enough. Let me make it bigger. Boom, boom, boom. There we go. So which one of these can't do stereoisomerism? Definitely A can. A can do it. So A is not the right answer because 1,2-dichlor. Oh, now these ones with the propane. Yeah, this is a bit of a cheeky question because I shouldn't have put this on here. I've only just realised. Never mind. Never mooned. I shouldn't have put this on it for what I'm covering today, but it no, 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 no. You've not fumbled. I put a bit of a difficult one on anyway. 1,2-dichloropropane. Let me show you why this one can do it. And you might be like, but sir, that doesn't have a double bond. Look, it's ANE. How can that do stereoisomerism? It's because I've been a little bit cheeky. I should have looked for questions where it said geometric, but they tend to combine both. This is an A2 question. So, you can have you guys done optical isomers? So you can be optical, or stereoisomers can be optical or EZ. So optical or EZ. Optical isomers are slightly different. They're the mirror image ones. And this one is going to be able to do a mirror image. So if I go 1, 2, 3, and we go 1,2-dichloropropane. So if we do that, this is going to be this one is going to be able to be an optical isomer. And why is this an optical isomer? Because this atom here, I don't know if you've done this yet. This atom here is a chiral carbon. It has 4 different groups attached. So it has a methyl here, a chlorine here, a hydrogen here, and then this group, which isn't a methyl, it has a chlorine in that. So it has 4 different groups attached. So it's a little bit cheeky. This question was really testing you on optical isomerism. Okay. Chiral carbons, yeah. So both of these can do, and this one, 1 to 3 dichlora, can do stereoisomerism as well. So when you have a double bond, you generally kind of, so you're looking at this one and going, no double bond, definitely can't be EZ. Can it be optical? And then if you draw it out, you'll see that it has no chiral carbon. So it can't be optical. And it definitely can't be EZ because it has no double bond. So that's the right answer. Let me actually get to one that's a little bit more relevant. Here we go. This one's a little bit more relevant. Which compound can do EZ? Which one of these can do EZ? Oh my good gosh. I don't know why I got like half my screen black. That doesn't make sense. How do I make this? Let's make this bigger. Half my screen's back. This is all gone a bit strange today, but there we go. Such is life. I've tried to make the image bigger. It's all a bit pear-shaped today, the live, but don't worry, it's all good. Back to normal next time. Right. Yeah, the one I had up previously was D. This one, we're looking at one with a double bond where it has, yeah, we just want make sure the carbon, see, it can't be A, because look, straight away, that's got 2 of the same groups. So we don't want A. That's got 2 of the same group, so you can quickly, and that's got 2 of the same group. Can't be that one because each carbon has the same groups on it. Each carbon that's around the double bond must have different groups. I think you're right. C. C, C, C. This one, no good. So I've circled the bits that are no good. So it's C. You're absolutely spot on. Well done. Good. Good, good, good. Well done, well done. Let's just give you a few more of these. Which compound is a structural isomer of Z-butene? It's a little bit tricky because talking about structural isomers. Structural isomers are a bit different. They have the same molecular formula but a different structural formula, i.e. butane and 2-methylpropane, right? So they have a different structural formula but the same molecular formula. Geometric isomers have the exact same structural formula. So what we're really looking for is something that has the same structural formula as this bad boy. So butene, if you were to draw out its structural formula, oh no, which one is a structural isomer of it? Well, it's not going to be B. That's a geometric isomer. So it's not going to be B. They have an identical structural formula. Their structural formula should be what? CH3. Uh, where's the double bond? Double bond's here, right? CH. Oh my gosh. Oh, I think I've lost the plot here. Yeah, something like, oh gosh, I don't even, I don't know what I've done there. Yeah, anyway, forget my structural formula, but whatever happens, these two guys have got the same structural formula, so they're definitely not. Which one is a structural isomer? Well, it's not going to be butane. They've got a totally different molecular formula, so can't be butane. Oh, cyclobutane has, yes, 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 yes. You're right, C. Remember, the cycloalkanes have the formula CnH2n. So basically, it's going to look different than that, but have all the same number of atoms. So yeah, I probably should have put, yeah, never mind. Okay, methyl but2ene. No, that's got 5 carbons. So no, that's not the same thing. Okay, Coolio. Right, let's see if there's any more. Let's do a few more of these. It's C. C, C, C. So let me go back and show you why it's not D for a sec. This one is 1, 2, 3, 4, 5. And then if it's methyl but2ene, I guess that's got 5 carbons, whereas these bad boys only have 4. So that's why that's not a structural isomer of it. It does have a different arrangement, but it's also got extra atoms. Okay. Oh, didn't we just do this one? Okay. Which alkene shows E to Z isomerism? Which has E to Z? Which has EZ isomers? So both of these are like, can you spot the EZ isomer in each one? What I would say, oh, I need to move that up a little. I've just seen that's not fully on the screen. No one likes to be off screen like that. All right. Okay. What I would say is that you might think, oh, I'm in A2, this isn't so important to me. But when you do your paper 3 in July, you're going to do your paper 3. You're going to, if you're doing AQA, you're going to have a big 35 questions of multiple choice. So right at the end of paper 3 is a massive multiple choice section with like 30, maybe I'm exaggerating, maybe like 30 questions. But there's a massive fat section at the end of paper 3. So you could well get these kind of questions coming up. It's where they're going to hit you with a lot of the ASE kind of stuff. C for the first one. Are you sure which one has... Let's try that. Let's try C. So that's propene. And now we're saying methyl propene. Here we got a problem. Check it out now. This carbon over here has got identical groups attached, and so has this one. So this can't be EZ, right? Oh, you can't see my fat face is in the way. Fat head is just getting... Whoa. Yeah, it can't be C. Oh, God. Let's not middle around with that. Piddle around. I was trying to change my camera. Yeah, shrink me. So it can't be C. Where are we going? Yeah, it can't be C. So A for this one. Let's check it out. Let's check this out. You said A important. Yeah, for this one. Let me check it out. So you're going... If we smash that there... Yeah. This could be EZ isomers, couldn't it? Yeah. This is like 1,2 dibromethene. So yeah, I agree. A. I'm going A. A for that one. Well done. For this one, I'm thinking pent1ene can, right? If you look at pent1ene, can pent1ene have them? No, pent1ene can't, because pent1ene is going to end up with HH. No, sod that. Pent1ene can't either. So no, not pent1ene. Ooh, 4-methyl pentuene. The moment your double bond is not at the end, you've got a good chance. So it's going to be A or B. Well, we know that. We've just cancelled out C and D. But I don't think it's going to be this one because of the 2,3 dimethyl. That's going to screw it up. I think it's the 4-methyl pentuene. There. Yeah, it's going to be that one. And the reason being, look, oh my days. It's painful watching me do this. Right, pentuene. You got 1, 2, 3, 4, 5. Put a double bond there, and you can see, look, I can have a hydrogen there. That's got an ethyl group coming off here. Oh, what did we say? 4-methyl. So if that's 1, that's 2, that's 3, that's 4. So I can put a methyl group there. Yeah, that's going to be a dodgy group there, but yeah, this can definitely work because you could have the 2 hydrogens there, and you could have this methyl group and this group down here. Yeah, so yeah, that's as long as you have 2 different groups attached to the same carbon, like carbon 1 and carbon 2, whatever. That's not really carbon 1, obviously, that's carbon 2 and 3, but you get what I mean in terms of the double bond. As long as you have 2 different groups on a double bond on each carbon on the double bond, you're sorted. Painful. Right, let's just do 2 more questions, and then I just want to do the difficult octahedral bit, and then we're done. Oh no, sod that. I'll tell you what, let's just look at this one, and then I'll do one more thing, and then I think we will finish up. We're going to just make it quick today. Okay, what's the name of this compound? See if you can name this one. And then, by the way, you can put up in the chat if there's any topics you'd like me to cover next Monday. I've been doing the poll, but I don't know if there's any particular topics people wanted me to go over. Like, are you guys in AS, or are you doing A2? Oh, that's it. I don't know. I've really got to sort my screen out. My screen's looking a bit bent today. It's not looking very good. Ay, ay, ay. Hey, people, hopefully no one's had any adverts today. I think I'm using the wrong live stream setting, because the last 2 lives I definitely had no adverts on, but this one, it came up starting at 2 o'clock, so I don't know if it's like a reset to one of my old ones which had adverts. So because I don't want no adverts on. The last 2 lives I didn't have adverts, because I can click a button which says no adverts. I don't know whether that works, but I didn't set it. With this one, I just went to one of my old lives from about 4 weeks ago and just clicked reuse the settings. So I think it's not got my new settings with no adverts. So I don't know. Anywho, what about this one? What are you saying for this one? B or which is the IUPAC name for this compound? Pretty dirty compound, right? Find the longest chain. So you're going to go 1, 2, 3, 4, 5, 6. So get rid of anything that doesn't say hex. Oh, look, they all say hex. And it's definitely going to be hex 3-ene. So we know this is going to be hex 3-ene. How do we know that? Well, there's 6 carbons, and the double bond, whichever way you number it, is on 3. So 1, 2, 3, or 1, 2, 3. So we know it definitely ends hex 3-ene. I don't really need a capital. Shouldn't really write that with a capital because it's not the start of the name, is it? So that would be dumb. Right. It's not a unique thing. So hex 3-ene, and then what we want to do is say, this is high priority, believe it or not. This might confuse a few people, but that is high priority. Why? Fluorine has an atomic number of 9, and carbon has atomic number of 6. So fluorine, beats carbon, and so that is high priority. However, this is low priority. Hydrogen has an atomic number of 1, and we have an ethyl group here with an atomic number of 6 on the first carbon, so we're going to call that high priority. And that means the two high priorities, and this is low priority, so the two high priorities are on opposite sides, all right? Or you could say the two low priorities are on opposite sides. Everyone cool with the fact that that makes it E, so it must be an E. Oh no, we not atomic mass. So what that means is low priority and low priority, they are opposite each other. So look, this is like trans, or we don't say trans with this. We're going to say E, meaning opposite, because the high priorities or the low priorities are opposite each other. So this means it's definitely going to be an E. And then we look, so it's E and it's hextriene, so it has to be A or B. And then we say, is the fluorine on 4 or is the fluorine on 3? We need to give it the lowest possible numbering. So we're going to go 1, 2, 3. The fluorine's on 3. I could number it from this direction, but that would give the fluorine a higher number rank than it needs to have. So I give it the lowest possible available ranking, and that would be calling that 3. So it's going to be A. I won't bother writing it all out. So E3 fluorohextriene. That's some messy. How do I clear that? Oh, I'm going to rub it all out. Right, I'm going to give you another one, and then I want to look at a couple of just things that lead on to let's do this one. This one should be a bit easier. Which compound? So what's the quick way? Remember, paper 3 A level, it's July. You want to save time. You want to be able to spot this. You've only got about 70-80 seconds per multiple choice question. Now, some of those titration ones and moles ones means you've got to do 3 calculations in 60 seconds or 90 seconds. Some of those about all where you do the CNMR. If they give you like 4 cyclic compounds and ask you how many different carbon environments there are, that's going to take more than 90 seconds. That's going to take you 2 or 3 minutes. So you need to get to these ones and save time. So it says which one of these can do EZ isomerism. So what we want to look at straight off the bat, we want to say, what ones can I cancel out straight away? If I have but1-ene, it ain't doing EZ, because when the double bond is at the end, what it means when the double bond's at the end, look, it's going to have 2,3-dimethyl-but1-ene. It's got 2 hydrogens, 2 things that are the same on the end of the molecule. So remember, we want different groups on the carbons. The 2 carbons that have the double bond, we want different groups on them. So I'm getting rid of A. So it's just a speedy way to do it. And then you're basically going, okay, but2-ene, I don't particularly like the look of that. If you draw the double bond and you say, right, here's my double bond for this one, and it's 2, so I know it's but2-ene, so it kind of looks like that. And then it says 2,3-dimethyl, so I'm like, oh, yeah. Immediately I'm thinking, no, I don't like this. 2, 3. Whoa. Oh, that means there's a methyl group coming off here. But2-ene. Yeah, that's got 2 methyl groups. They're going to be identical. Oh, that's taken me forever to do. But anyhow, normally when you've got so many things like 2-ene and you've got 2 used here, that doesn't look good. I like the look of this one maybe the best. What do we think? I like the look of 3-methyl pent2-ene, and the reason being the double bond and the side group are on different things. That doesn't mean it's immediately cert, but I'm preferring that as a look. So what I'm going to say here, why would I immediately go for this one? So if I was speeding the question, I'd immediately go get rid of the one where the double bond is at the end, because likely it's got the same groups attached. Then I would look and go get rid of the double bonds where the numbering of the double bond is the same as one of the side groups, and the side group is a carbon, like an alkyl group. So if you have an alkyl group attached to the same carbon as the double bond is on, then the likelihood is that may well not do EZ isomerism. So the quick way to do it would be, if we look at this pent-2-ene, pent-2-ene is telling you that the methyl group is on the third. So immediately I know this is going to be, look, it's got an ethyl and a methyl. That's two different groups attached. And then this bad boy has got a methyl and a hydrogen. So that one is cool. That can do EZ. But that you will get to the point where you can spot it, because you're like, it's got a double bond and the double bond's not on the first carbon. So pent-2-ene or pent-3-ene can do EZ. And the side group is not on the same carbon like as the first double bond. Anyway, yeah, there's just like a few little things like that you'll get to. All right, last thing I just want to go over before I finish up, just real quick, is when you do A level, you do A2, you're going to come across geometric isomerism with your complex ions. Now this is an octahedral structure, and weirdly, if any of the groups are 180, so these two identical groups are 180 degrees apart, we say that it's trans because they're either side of the metal ion. But here, where they're 90 degrees apart, we say that's cis, sisters. So there's just a different rule. This is cis and trans isomerism in sort of complex ions, and they have a slightly different rule. So trans is when they're 180 degrees apart, and cis is when it's only 90 degrees apart. You might say, but sir, isn't the ammonia 180 degrees apart as well? Well, no, the ammonia is always 90 away from another ammonia. So in here, ammonia is always 90 degrees away from another ammonia. So we're really looking at, this is known as cis. This is known as trans because you've got two of the same atom 180 degrees away from each other, and there's none of them are 90 degrees away, so we call that trans, and this one is cis when they're 90 degrees away. Anyway, that's a little bit complicated, isn't it? You get the same thing though. You get square planar as well, like cisplatin and stuff, which is a cancer drug. You're going to do things like that when you do complex ions, and again use the same rule. Yeah, but we'll come to that another time. That's just showing you that it does continue into A2 a little bit, this geometric isomerism. Anyway, we're going to finish there, folks. That was just a quick little crusty little live. Anybody who's doing bio, is there anything anybody wants to do on Thursday? I'm going to do a bio lesson. So if there's anything anybody wants to do on Thursday for biology A level, I am going to start GCSEs I think on Sunday, but that's not relevant to A level students. So anyway, that was a little bit on EZ isomerism. So I hope it helps, and I hope you're working hard. Remember, if you're doing A level chemistry, success in A level chemistry is going to be based on you guys putting the time in. Like if you're in A2, you still got the chance to get an A star. But even at this stage, but you're going to have to commit. Like the way I see it, if you do 5 hours a week on A-level chemistry and you do 5 hours a week on A-level biology externally from your study in school, you're going to smash it. But that is a solid 5 hours. So whether that means that you do for your A-level chemistry, that means when you get home you're doing an hour of pure A-level chemistry 5 hours a week. Now you could do Monday to Friday, but that I know some students that do that, and they do that for all three. They have 3 A levels and they do 3 hours a day when they get home from school. But why do that? That's going to kill you, right? With dinner and everything. but you can do some of those hours on the weekend as well, but that's a minimum. So if you're doing 3 A levels, you need to be putting in a mins 15 hours if you want to get top grades. So like, and that's externally from what you're doing within college or school. You got to have a minimum 15 hours, so 5 hours per A level really, if you want to get an A or an A star. And then if you put 5 hours in per A level per week externally, it's hard not to get an A star. And you've got to be smart with that revision. So you pick a topic, you pick one topic, and you say like, I'm working on that this week, and you put 5 hours in. So you're going to learn the theory, construct some revision cards for that topic, practice it, and then spend a couple of hours doing practice questions, either online, you know, or whatever resources you can. And that means you'll smash your A levels. All right, guys. Coolio. I will see you next time. That was just a little crusty session. Take care, and I'll see you again.
You're still here? It's over.